Now we're going to see how we can do central limit theorem computations in the calculator as well, where this is actually very similar to what we did in 5.1 and 5.2 in terms of normal CDF computations. It's just our input is going to be a little bit different for some very important reasons. So looking here at this example, what we have is behavior for 50 drivers age 16 to 19, and we want to talk about the behavior of the mean. In particular, I want to see what the probability is that the mean is between 19.4 and 22.5 miles, where we have some assumed standard deviation. And assuming you know that standard deviation is a bit unfair, but we'll talk about that more later on. Anyway, what's important to note here is we're not trying to make some determination for the behavior just of values, of some selection of teenagers. We're looking at the mean of a sample of 50 of them. We're trying to make a determination about the behavior of the entire group as a whole, which for one is a different sort of result than we'd be getting just talking about single people, but it also allows us to look at this in terms of the normal distribution, even though we don't know for sure that this behavior here is normally distributed. It gives us more leeway to talk about these things. So we get to talk about perhaps a larger thing, and we also get to apply our information to more broad things, because we don't know that this has a normal distribution, but because we're taking a large enough group, we can say that the mean is going to be normal enough for our purposes. Anyway, to do this in the calculator, what we're going to do is recognize our values here. So we're going to go second vars for distributions and go back into normal CDF, where now we have a lower boundary of 19.4, an upper boundary of 22.5, and here the mean that we're looking for is really a mean of sample means, mu sub x bar. We can't tell the calculator to specifically look at that, but mu is close enough for the case for what we need. So we're going to say the mean is 20.7, just bearing in mind that that's actually a mean of sample means, at least in this case. And for sigma, the standard deviation, it's not enough to just take the value of 6.5 here. And the reason for that is when we're talking about the behavior of a mean, because a mean takes into account usually many values, in this case 50 values, we want to notate the fact that it has a lot less variation than just the single value. So instead of the standard deviation 6.5, we divide by the square root of the sample size 50 to get the standard error. But again, calculator doesn't say that's sigma sub x bar, it just says it's sigma. We just have to bear that in the back of our minds, which is about 0.9, but when we put it in the calculator, we can be a little bit more exact. Thing is, though, when we want to be a little bit more exact about finding this type of behavior, something kind of odd happens. And we see that for the value we get, well, it's close, but it's actually off by a little bit. It's off by, let's see, what would those be? About 5/10,000ths. It's not a great deal, and it should be close enough for the homework assignments, but it's important to note that we do get differences like that on occasion, especially when we're putting in our values more exactingly. And there are, what's the word I'm looking for? Non-perfect squares in our sample size. That is, in this case, we have to recognize our sample size was 50, which is very much not a perfect square. So this 6.5 over root 50 would be a really nasty decimal that if we use the table, this sort of method, we have to follow through on some rounding and take a subtraction, whereas the calculator can just run it directly. So we get a slightly different answer. And it should be close enough, but just bear in mind that we can have some differences. For our next example, we're talking about mean room and board expenses, where in this case we have the mean expense is $10,453. We're looking at a sample of 9 four-year colleges, and we want to find the probability that we get expenses less than $10,750, where we're assuming approximate normality and a standard deviation of 1650. To do this, again, we can run it through carefully like so by hand, or we can run it in the calculator where we do second distribution, normal CDF, where our lower boundary is just something very, very small and negative, or very, very large and negative, excuse me, to say that we're going off as far down as we possibly can. Our upper boundary here is that value of 10,750. Our mean, in this case, we're going to say it's close enough to talk about it in terms of mean mu in place of the mean of sample means mu sub x bar, so 10,453. And our standard deviation will be taken in instead by sigma sub x bar, the standard error. But in this case, it actually is a perfect square, and we're dividing that perfect square into a thing that happens to fit into nicely, so we really do just get the value 550. And putting that in there, running our numbers, we actually don't have as much of an issue with rounding error. We just get the desired probability, because it happens to fit into a nice pattern here. Now for this last example, we're going to do something kind of important where we're going to compare what happens in terms of mean behavior with what happens in terms of single value behavior. Where for our first part, we want to find the probability that a randomly selected student pays less than $1,400, where we have that the values are normally distributed with a mean of 1615 and a standard deviation of 550. So this would be a classic question like in 5.2. So that's a normal CDF, where here we're going up to 1,400, so we have that negative large value, where you do have to be a little bit more careful here with how large that number is that you put in, because we're talking about big things to begin with, talking about things in the thousands. Our mean is 1650, and our standard deviation sigma is 550. And remember, here we're talking about a specific value, so we do just get mu and sigma instead of the sub x bar jargon that we have normally for this section. But we run that, and we're going to get a value here of, again, up to some rounding, about 0.348. Meanwhile, if we instead talk about this in terms of a mean amount, one big thing is going to change in our input, and that's going to cause a large effect on our output. We're going to go back into normal CDF. We're still going from negative infinity to 1,400, and our mean of sample means stands just as well with our mean of 1615, but our standard error here is not just the standard deviation. We have to divide it by the square root of our sample size 25, where that is a perfect square, and it's going to knock down to just being 110, but let's be careful here anyway. And we're going to run that, and now we get a probability of about 2.5%, which is to say it's considerably more unusual that you get a mean, sample mean that is that far away, that is that low in this case, than just getting a single value that is that low. And the reason for this is a big part of what goes on in 5.4. That is, when we're talking about variation for single values, it should be much larger than variation for overall central behavior of an entire group, especially a group with more items in it. That we have 25 things as compared to 1, there should be a lot less variability. The values for a sample mean should be a lot more consistent than the values for a single drawing. And that's what these probabilities show us.